Swayam Prabha. Digital India. Educated India.
Welcome to week 5, lecture 4 of the NPTEL course on Muffler acoustics. So, if you recall, in the last week we were just about to derive the transmission loss of a generalized Muffler elements in terms of the 4 pole parameters or the T matrix parameters. So, the idea was that once we have a general expression for transmission loss in terms of the T parameters T11, T12, T21, T22 and so on, then we can probably consider the special case of extended inlet and outlet mufflers and go about doing the transmission loss analysis. So, to this end what we will do is that basically put P1 tilde V1 tilde is equal to T11, T12, T21 and T22. So, P2 and V2. This is what we are going to get. Now, recall that actually when we consider such an element, we have we have the implication or the implementation of anechoic boundary conditions to for the transmission loss setup. So, you have this kind of a thing. So, you have an echoic termination. So, the waves, let us say the waves A1 wave is incident here and B1 goes here and A2 goes here, but B2 is not allowed to come back because it is an anechoic termination. So, you get B2 equals 0. This is what we are going to get. So, we have this. Now, P1 tilde is A1 plus B1 and V1 tilde is A1 minus B1 divided by Y1. Y1 is the characteristic impedance of the exhaust pipe, let us denote it by 1, and obviously we will do some special cases where the exhaust pipe and tailpipe have the same diameters, that is to say they have the same characteristic impedance, and A2 P2 is nothing but A2 and like this. So, what we are going to do is basically substitute these expressions here and then worry about what happens next. So, A1 plus B1 and A1 minus B1 by Y1 is equal to T11, T12, T21 and T22, and this is A2 and A2 by Y2. So, A1 plus B1 is equal to T11 plus T12, and here you have your this is Y2. So, this becomes equal to A2, this becomes equal to A2. So, you get 1 here, let us call this equation 1, and what about the other one? A1 minus B1 by Y1 is equal to T21 plus T22 divided by Y2 whole multiplied by A2. So, what we probably could do is simplify this further, and to that end we multiply both the sides by Y1. So, remember there was a Y1 here. So, we multiply both sides by Y1 to get the following, which can be nicely simplified or written in a more cleaner manner by the following expression. This is 2. So, obviously, we need to find out what do we need to do? We need to find out A2 and B1 as a function of some function of a1. So, it is simple, add 1 and 2 to get 2 times a1, because when you add this one equation 2 and this one, plus b1 and minus b1 gets cancelled, and you are left with only a1, and what we get is basically T11. So, we get a nice clean expression T11, and the contribution from this side is T12 divided by y2 plus T21 and into y1 and into y1 by y2. So, this is A2. So, remember, for getting the transmission loss, all we need to do is basically evaluate the following: A1 by A2 is equal to T11 plus T12 by y2 plus T21 into y1 plus y1 by y2 into T22. So, this divided by half is your this thing. So, what does it tell you basically? It tells you that the ratio of the incident wave amplitude to the amplitude of the wave that propagates downstream into the anechoic termination is nothing but sum of the T matrix parameters, and obviously some of the parameters are multiplied by the characteristic impedance or the ratios, and half of and multiplied by a factor half. So, all we really need to know for getting the transmission loss is really this guy A1 by A2. Why? Because if you recall the discussions in the last several lectures, last week I guess, this was ratio, transmission loss was nothing but ratio of the acoustic power that is incident to that of the acoustic power transmitted downstream. So, this can be very nicely written as A1 mod by 2 rho naught by say y1 and A2 mod by 2 rho naught y2. Okay. So, we get this sort of a thing. So, what it means is 10 times log 10 and mod A1 by A2 mod square and y1 y2. So, y2 would go up, y1 would be here, and this would be 20 times log 10 and mod A1 by A2 and y1. Now, basically everything reduces to the substitution of well, let us say equation 3 in the above expression. So, what do we get then? We get 20 times log half of T11 plus T12 by y2 plus T21 into y1 plus T22 y1 by y2, but remember you also have root over y2 by y1 sitting here. So, this would be somewhere here, and the entire thing mod. Let us quickly see what are the special cases that these expressions can take if we go about simplifying this. What are the special cases that we can get? So, one way of writing the entire thing would be TL is equal to 10 times log 10, and the idea is to eliminate that square root factor. What we probably could do is get this thing in the following form: T11 plus T12 by y2, I guess y2 plus T21 into y1, and this is y1 by y2, and this entire thing is divide by 2, and this is y2 by y1. square. Now, y1 and y2 are the characteristic impedance of the inlet port, inlet. Of the outlet port. This is outlet. So, what it probably means is that if we have y1 equal to y2, y1 equal to y2, then things would simplify, and let us call this as y naught, as we were doing it for the extended inlet and extended outlet element. So, under this situation, transmission loss then becomes 20 times log to the base 10, and this would be y naught, and this would cancel out, and so would this term, or probably this term would be unity, this term would be just be 1. So, so you get basically T11 plus T22 plus T12 by y naught and T21 into y naught, and what you get is 2. So, we get this sort of a thing for the transmission loss of any general element, but with the condition that inlet, this is D naught and this is also D naught, inlet and outlet are equal. So, we have, once we have this condition, then of course, your things would simplify a bit, and probably as we go deeper into the analysis of such expressions, transmission loss, we can actually show that transmission loss and insertion loss are equal in the limiting case of the radiation impedance, or basically the instead of exposing the outlet pipe or the tail pipe to the atmosphere, if that were to be the if that were directly fitted to the anechoic termination, insertion loss will tend to the transmission loss under the limiting conditions of anechoic termination. So, we can easily show that, and actually there are large number of things that we could probably study here. One of them being, if we have, look, this is a generalized expression in terms of general T11, T22 and all the T parameters, also known as the 4 parameters like I was mentioning. But although we will revert back to the extended inlet and extended outlet case in a while, but what I am trying to tell you guys here is that if you have a general element like this, a simple expansion chamber, or you suddenly have a bigger chamber like this, but with things like extensions or maybe with perforates, we haven't really discussed that element now, but perhaps we could do. And actually you could have a thing like a small slit here, and this goes here, and there could be a resonator, something like this. You could have all sorts of complication, different elements. So, with the understanding that there is a uniform unidirectional propagation of acoustic power. So, well, under such a situation, what we really get is that the transfer matrices can be cascaded. That is to say, let us say this is the transfer matrix for this element is 1, this is element 2, because now this length becomes important, although it is uniform, because it is connecting two different muffler elements. So, and this is 3 and so on, and we have transfer matrix between this point and this point, this point and this point, this point and this point, then it is T11 times T22 into T3, T is equal to this. So, we have this sort of a thing. So, once we obtain the overall transfer matrix by sequentially multiplying the transfer matrices of individual elements, we can use possibly the generalized expression like this, the one here, let me call this as number 4, equation number 4, to find out the transmission loss of the overall system. Okay. that we can do. But remember one thing, all this while we haven't really considered the effects of mean flow, which is important in lot of practical applications. So, we have to account for the convective effects of mean flow in the expression for evaluating the transmission loss, and that would also show up in the T matrix parameters. But for now, what we will do in the remaining part of this lecture 4, that is that revert back to the test case of our element that we promised to study here, the transmission loss. So, let me quickly go to Maple and probably show you some expression, and we can first we will discuss some qualitative features. Why are we getting, or why should we anticipate a peak at certain frequencies, and probably relate it to the troughs or the resonance frequencies of the chamber in all. So, let us go to Maple then. We are in Maple, what we were discussing in the last class, last lecture. Look at the individual elements. So, you know the one that is highlighted here, I am so sorry, let us say T5. So, if I type T5 1 1, well, we get this. Now, we need to every time we open a Maple script, Maple file, we need to restart or rerun it again. So, that all these expressions, the ones that are validated before this particular expressions, are also evaluated and known to the function or to the program. So, now we get this T11. Let us nicely write down all the T matrix parameters sequentially. T12 is like this, and T5 to 1 is like this. This is a bit nasty expression, and but nevertheless important. So, each of these 4 pole parameters are there in front of you. Now, based on the transmission loss expressions that we just saw just now, it was basically a summation of T11s and T12, T21, T22, obviously scaled, some of the expressions are scaled by a certain factor. Now, does not matter, those were basically your Y naught terms, I reckon, Y naught or the inlet and outlet pipe. Now, let me go back to the slide here. So, here you are, you have your T11 term, let me underline it with the orange color, T22 terms, and T12 is divided by Y naught, which is your characteristic impedance of the port, and while T21 is multiplied by Y naught. What does it mean? Let me get back to the Maple script. Now, recall T5112, this is your element T12, and it was divided by Y naught, and in the numerator we have Y naught. When you basically multiply this out completely, Y naught will tend to cancel out, leaving us with only the sine k naught L3 term divided by m into j or I. Okay. T521 or T21 is basically has a contribution of Y naught in the denominator, and in the transmission loss expression it is multiplied by Y naught. So, this term will eventually cancel out, all this will sort of cancel out, and T22 probably will not have such a problem. So, basically the idea is just a summation of these expressions when in the transmission loss when you sort of do that. So, if we were to simply divide this by Y naught, and we need not ask it to simplify, but and similarly we can sort of multiply this by Y naught, and this is like this, and let us call an expression exp1, and which is just nothing but the summation of T511 and your each of these small expressions and this one so we get this thing, and let's multiply this by 0.5 or half. Probably a better thing would be multiply this by half and go about doing things. So, this is your expression that you get. This is eventually we need to take the log of this this TDS expression, log of this expression to the base 10 and multiply it by 20. So, all those things are good, but just looking at this expression, I guess we should be able to tell something about where the peaks could occur and whether they can annihilate the troughs. So, T 5 to 1 multiplied by y naught. So, let me try to do something about this one, T 5. So, this gets multiplied by y naught. So, once you do that, we are getting y naught here. That shouldn't really be the case. Possibly we can get rid of half here and try to go about so y naught still occurs. So, why is that so? So, basically what we intend to do is that simplify these expressions T 5 1 1, T 5 1 2, T 5 2 1, T 5 2 2 as much as possible, and as I have been mentioning, we need to is basically the addition of these terms and they are being suitably scaled. So, one clever trick that we probably can figure out, look, the thing is that this is multiplied by y naught. So, y naught is coming out here, but when you simplify things becomes even more it becomes a little more tedious. So, basically one clever trick of getting rid of y naught in the denominator, look, this is bound to be cancelled, the term in here and the term here, this will get cancelled. So, basically if we substitute y naught is equal to 1 and directly add up all these terms, so we will be getting expression 1. So, this is the entire expression, if we recall, of the argument of logarithm in the transmission loss expression. Obviously, there is a factor of half also, which I have purposely omitted to keep things simple, because all the dynamics, all the system behavior can be reflected by considering or simplifying these terms only. So, what we do is that once we substitute y naught is equal to 1 here and simplify, we see y naught term in this thing has completely gone away, and m is nothing but the ratio of the cross section area of the chamber without any extensions to that of the port. In other words, it is the square of the ratio of the diameters. Now, we probably can simplify expression 1, but then a better way we will be getting this thing. So, there is no point, or it is probably a little too much. So, what we will do, probably put expression 3 here and substitute L 3 is equal to L minus L 1 minus L 2. That is to say, we will substitute the intermediate length L 3 as a difference of the neck extensions L 1 and L 2. So, we will put that here and substitute that in the numerator NUMER here, what I am highlighting now, this term, this is the numerator of the expression 2, which is step above. So, we substitute L 3 is equal to L minus L 1 minus L 2 and in this numerator expression, that is this thing, and combine trigonometric terms, because this is going to be a little tedious algebraically, and then collect terms in the order of m. That is to say, now if you basically have a look at this expression, we will get the following, where m square is the term associated, leading order term associated with sin k naught L, that is L is the capital L is the chamber length, and you get other terms. Denominator is much simplified, but very important, which is cos k naught L 1 times m into cos k naught L 2. Before we move ahead, we need to carefully analyze the numerator, simplified numerator part and the denominator part, where we have actually we now have only a few parameters or dimensions at our hand, at our disposal, namely L 1, L 2, capital L, that is the chamber length, frequency of cos k naught, and the expansion chamber ratio m. So, if we carefully, now all this while I was saying that by putting the impedance right at the interface of the extended inlet and chamber junction and extended outlet and the chamber junction, by setting the impedance as 0, we can get the attenuation, we can get the resonance of the annular cavities, and that is where the peaks will occur based on the plane wave limit. So, why is that? Because this transmission loss argument consists of this entire big expression divided by the denominator. So, when the denominator is going to 0, that is cos k naught L 1 is equal to 0, we are getting the peaks due to the first annular cavity, that is the extension peaks due to the extensions at the inlet. Similarly, cos k naught L2 is equal to 0, the highlighted term here would basically give you the attenuation peaks due to the extended outlet part. So, that is the formulas are now it should be very clear. It is your k naught L2 is equal to 2 n plus 1 whole into pi by 2. So, you can evaluate all those resonance frequencies for the extended inlet as well as for the extended outlet. Now, important question here is that what do we do to tune the peaks? Tune the peaks with the troughs or the first and second resonance frequencies of the chamber. So, for that we have to look into the numerator, and there are some special cases of course. So, now the first axial resonance or the trough due to the first axial resonance will occur when k naught into L is equal to pi. So, we substitute k naught L is equal to pi in expression 3, which is the numerator given above here, and combine again, follow the standard procedure, that is to combine terms using simple trigonometric identities and then simplify and collect terms in the orders of m. So, after all this algebra, which is fortunately done by Maple, we do not have to worry about it. We get a much more simplified and a manageable expression. So, a special case, of course, I would like to point your attention towards a special case when when there is no extensions, that is L1 is equal to L2 is equal to 0, that is it is a simple expansion chamber. So, what do we get? We get this is 1, this is 1 and this is just n, denominator is just m. Now, what happens to this thing at the first resonance frequency? We get this term is minus half because this term goes to 0 and this term actually cancels out, and so does this term. So, these two terms basically cancel out, the ones that are highlighted here, but these two terms are minus half and minus half because cos of 0 is 1. So, minus half minus 1. So, you get minus 2 times m, and these two terms, this term will go to 0 again because sine of 0 is 0, and cos this entire term will be minus half, but there is also half sitting here. So, that will cancel. So, eventually what we are left with is basically minus 2 m in the denominator, I am sorry, in the numerator, and m in the denominator. So, so basically m gets cancelled and you are just left with minus 2, but you are taking a mod of that. So, it is just 2, and in the denominator there is also 2. So, eventually you are getting log of 1 to the base 10. So, that is how you are at first axial resonance frequencies. In the limiting case, when L1 and L2 is tending to 0, we are able to again retrieve back the case of simple expansion chamber, and that is important to validate our expression. Now, let us see what we are getting here. If we substitute 2 pi, that is your second axial resonance peaks, basically the same argument would apply. Here we are able to cancel these two terms, but this term and this term will be half. Half is 1, 1 plus 1 is 2. So, 2 times m, other terms will cancel out. So, 2 m and in the numerator, m in the denominator. So, again the same logic, log of 1, that is 0. Like this we can do it for any integer number 3. If we do, we get the same thing. If we do it for 4, we again get half. Like this we can keep on evaluating for the special cases. Now, it is a bit difficult or a little bit tedious to work out from just this expression, that let us consider that L1 and L2 are non-zero in general. That is to say, the chamber has a certain extension, it need not be equal to L by 2. If it is L by 2 and L by 4, then it will be very interesting to see that when it is L by 2 here and this is L by 4 here, and k naught has a certain frequency. So, it will so happen that the numerator and the denominator will behave in such a manner that the transmission loss argument of the logarithm will never be equal to 1. If that is to say, it will be a large quantity, and that is why you get a peak there, a very sharp peak, transmission loss theoretically tending to infinity. So, that will happen when L1 is equal to L by 2, L2 is equal to L by 4, and for the frequencies pi, k naught L is equal to pi or 2 pi or 3 pi. However, at k naught L is equal to pi, but L1 is not equal to L by 2, you would see that theoretically you would be getting a peak. So, although it is a bit tedious to explain it using here, we have done decent in terms of explaining the basic behavior of the extensions, what extensions can do in terms of uplifting the trough. So, now I guess it is the time to go to a MATLAB code that was written here. Let me work out the MATLAB code. So, what we do basically, let me explain to you very quickly, but in a sufficient details, we write MATLAB. MATLAB, like Fortran or C, is a programming language especially useful for all scientific calculations. It is possible that a lot of you would be acquainted with MATLAB. It is very easy to use language, and a lot of inbuilt commands are there which makes matrix multiplication or certain linear algebra operations very simple. So, the name of MATLAB in fact it is matrix laboratory, MATLAB. So, what we do, we write functions to evaluate certain quantities, and each function will invoke the another function. So, let us do that. So, here we are writing a function to plot the transmission loss plot, that is the name of the function file. It is calling two parameters, the upper and the lower limit of frequency, inlet and outlet pipe diameters, that is your port diameters or radius, I am sorry, length of the chamber, length of the extension at the inlet, that at the outlet, and I guess D1 and D2 are pretty much the same as inlet and outlet respectively. D is the chamber diameter. So, basically by suitably setting all this, we can get the transmission loss plot. So, transmission loss then is basically, we assume a standard atmospheric conditions and density and all that. So, we evaluate the sound speed and inlet outlet pipe characteristic impedance, and then there is a function file to evaluate the transmission loss transfer matrix for the extension in inlet and outlet, that is basically based on cascading. And this is the expression that we have been talking about all this while, sum of the T matrix parameters scaled by certain characteristic impedances. So, this is something that we have been discussing. So, I will quit this part and directly move on to the function that computes the transfer matrix. So, as usual, we have your length of the chamber, extensions at the inlet, outlet, diameters of the inlet outlet pipe, which is equal to that of the R underscore inlet and R underscore outlet respectively. Frequency is a given frequency at which the transfer matrix parameters have to be evaluated. Remember, transfer matrix parameters are functions of frequency. So, here it is a simple cylindrical tube. So, we know the transfer matrix for the portion of the inlet pipe where this is evaluated, and similarly TC1 is a cylindrical tube where basically the chamber is evaluated. So, probably this for the cavity, I am so sorry. So, by doing all these, by suitably multiplying the transfer matrices T12, TC1, so we evaluate the impedance here, and T23 is the transfer matrix at the sudden area expansion due to the extended inlet, and L3 is the length of the propagation length in which the protrusion is not there, and we evaluate the transfer matrix for that portion, and this is again that of the cylindrical pipe, and we are doing nothing but sequentially multiplying points 1 to 2, 2 to 3, 3 to 5 and all those sorts of arrangements. Here of course, we do something like evaluate the impedance at the extended outlet. So, then this transfer matrix is basically passed on to this function, and I guess we are in a good position to do report some parametric studies. So, what we will do basically is that we will basically write down certain things. Let me increase the screen space for you. So, let us consider some realistic dimensions. Frequency, let us start with 5 hertz and move on till say 2000 hertz, it should be good enough. In R inlet, so let us say this is 25 mm, divide by 1000 because to convert mm to this thing. Length is 500, let us say the length is 500 mm, and L is 250 mm, L1, and this is 125 I guess, and this is also, let us say this is 50 mm because that was 25 and so was this, and diameter of the chamber. Well, typically automobile mufflers have a diameter, maximum diameter of say 300 mm or 350 mm max. We will consider 300 mm, it can go from 150 to 300 or so, and this is just the color in which the graph will be plotted. So, what we will do is that set the frequency parameters 5 hertz is the lower frequency limit, 2000 is the upper one, 25 mm, these are the two ones at the inlet and outlet pipe extensions. These are the same as the diameters of the inlet and outlet pipe. 250 mm is the length of the extensions at the inlet, and 125 mm is the length of the extension at the outlet, and 500 mm is the total length of the chamber. So, the intermediate length where there is no protrusion is given by 125 mm, basically capital L minus L1 minus L2 small, and 50 mm each is the diameter of the extensions at the inlet and outlet, and 300 mm is the diameter of the chamber, which is typical of that of commercial automobile. The maximum diameters that are used in commercial automobile mufflers is about 300 mm or so. In some cases it might go up to 325, 350 mm, and it ranges from 150 to 150, 175 to all the way up to 350 mm. So, we choose about 300 mm as the diameter of the circular muffler, and let us see what we get. Well, we get the following thing. So, if we notice carefully, this was the frequency at which the trough would have occurred. So, we could actually do the following just to make the explanation perhaps a bit better. What we could do is that we could quickly write some non-dimensionalize the frequency 2 pi times f by sound speed, which is 343. So, we will probably put it 343 times L. So, 2 pi, so non-dimensional, so non-dim. So, once we do that, let us see if our life is improved. So, we get this. Okay. What do we see here? We see that if we go to the cursor thing and put our mouse here, we get the peak almost at 3.14 k naught L is equal to pi. So, that might just be because of frequency scaling. So, we get almost at, we are able to almost kill the trough that would have occurred at k naught L is equal to pi if the extension was not equal to L by 2. Similarly, if it was because of the fact that it is L by 4 the extension at the outlet, we are able to kill the second thing, which occurs at 2 pi, that is 6.28 or something like that. So, what we will do is that we will keep this figure as it is. Both the extensions at the inlet and outlet have been tuned, and we will basically purposely mistune or consider a non-tuned extension. Let us say we put 225. So, we see let us put grid on, so we can look at the grids, and so you see we are getting a trough here, So, this trough occurs at 3.14, close to that, and that is because the length of the extension is less than L by 2. So, naturally based on the plane wave limit, the frequency thing is pushed up. So, now let us consider a couple of more parametric studies at the inlet. Let us name this as use another color. Let us, instead of 225, let us say we put it at 200, and let us see how bad the results are. We still get the trough at the first actual peak, and this peak shifts towards the right because the chamber length now is, the annular cavity length is less. This is green, and your now on the other hand, if we consider an increased length, say 275, we will see the peaks occur slightly before the trough. So, there is a shift in the peak, and if we consider a further extension length, we will see the peak occurs at even lower frequency. The point being is that there is a mistuning, or the axial resonance trough, or the first axial resonance trough is not coincident with the first peak of the quarter wave resonator formed at the extended inlet. So, that is why it is very important to tune it to match the trough at the first axial resonance, and then that is how we will be able to completely kill or eliminate the trough at the first axial resonance peak. So, by choosing the extension at inlet L1 equal to L by 2, we are able to completely annihilate the trough that would otherwise occur if the extension was not tuned. And the similar logic will apply for the extensions at the outlet, that is at this point. If we choose a length different from L by 4, we will see a sharp trough occurring here. So, and also notice that when you are getting a peak here, this peak, when I am pointing my mouse, so you are also getting the peak somewhere here, that is your third thing. So, we are able to cancel two troughs, the trough due to the first axial resonance and third axial resonance, but the fourth one is not being able to improved even when we have L by 4 extension, but the fifth one we can improve. So, this is what we basically get by this extension. So, with this parametric study, I guess we will stop in this lecture. It was a bit extended lecture, and we will meet for a little shorter lecture in the final lecture of this week, that is lecture 5 of week 5, where we will probably discuss about some other typical elements used in mufflers, such as mufflers with side inlet and side outlet. And also, before we begin that, we will probably have a very briefly review this particular extended inlet and outlet element with regards to higher order plane wave theories, make some comments essentially. So, with this I would end here, and thanks a lot for attending. Stay tuned.